Hello everyone. This next part of this lecture series is all about off-grid system design and calculations. Part Solar power system basic design and calculations. Part 4 of 5 off-grid system design and calculations. The off-grid setup is composed of four major components. We have the solar panel array, solar charge controller or SCC, battery bank, and DC to AC inverter. The off-grid system design requires more steps as compared to the on-grid setup. So here are the steps. Step 1, that will be the load analysis. So assuming that this installation is on a very remote area and far away from the power grid, we will take a different approach as compared to the on-grid setup. On-grid setup load analysis, because here we don't have any monthly electricity bills, where we can just easily take the monthly power consumption and divide it by 30 days. So we'll take a different approach for the load analysis for an off-grid setup. Step number 2 would be the sizing of the solar PV panels. Step number 3 would be the sizing of the battery bank. Step 4, we'll size our off-grid inverter, and step 5 we will size our solar charge controller. Step 1, load analysis. So for the load analysis for an off-grid setup, it's quite different. Here you need to list down all the electrical equipment inside your house. And for this example, suppose we have LED lights, LED TV, electric fans, a fridge, a laptop, and a washing machine. After you have listed so you have listed down the equipment, then next step is to list down their individual power consumption. So you can find this information at the packaging or on the label at the back of your equipment. In this example, the LED lights consumes around 9 watts, the LED TV around 80 watts, the fan around 65 watts, fridge is around 250 watts, laptop 80 watts, and the washing machine around 250 watts. So next one, after you have listed down the unit power, list down their quantities. So for example, we have 4 LED lights, 1 LED TV, 2 fans, 1 fridge, 1 laptop, and 1 washing machine. Then next step is to multiply the unit power right here by the quantity to get the total power consumption for each type of equipment. Then next is we list down the duration at which this equipment will be used. So for example, the LED lights are to be used only at night, so we'll assume that will be around 7 hours. LED TV for 5 hours, the fans for 8 hours each, the fridge for 10 hours. Yeah, there's a question here, but why not 24 hours for the fridge? The reason being is that because once it reaches a certain temperature set by the user, it won't use as much power to maintain this temperature. That's why we have only listed 10 hours operation time for the fridge. So laptop around 4 hours, and washing machine 2 hours to do the laundry each day. Okay, next one, we will multiply this total power by the duration, and yeah, we multiply this by this. We have the daily consumption for each type of equipment, then we sum this all up, and that will be the approximate daily consumption of our equipment. So for this example, we have around 5 kilowatts power consumption per day. Next step is sizing of solar PV powers. So now that we have calculated how much power we can consume daily, you will also need to determine how much sun is your location getting, or what we call the sun peak hours. The sun peak hours is the duration at which the intensity of sunlight is at 1000 watts per square meters. So the average sun peak hours is usually around 4 to 5 hours, and that value varies as you move away from the equator. So there are locations where they have longer days and some will have longer nights. So this piece of information, you will have to do it by yourself. You have to just Google it. But if you just wanted to do some estimation, you can probably use 4 hours or 5 hours. That should be quite enough. So to compute for the required capacity of our solar panels, we should divide the daily consumption by the sun peak hours and multiply by 1.3. So that's around 5, yeah. So that's 5 kilowatts divided by 5 hours, multiplied by 1.3. So the required PV power is around 1.3 kilowatts. Now suppose we have a solar panel in mind. One of them is this panel right here, with a power rating of 380 watts. Well, to compute for how many of this type of solar panel you need for this installation, you just need to divide the required solar PV power, which is 1.3 kilowatts, and divide it by the solar panel rating, which is 380 watts. So we have 3.43, or rounded up, we will need four of this 380 watt solar panel. Step number 3, that will be sizing the battery bank. So the battery bank capacity depends on 4 factors, namely the daily power consumption, the depth of discharge or DOD of the battery, the efficiency of the battery, and lastly the system voltage. The depth of discharge, DOD, That is the allowable level at which you can drain your batteries. So over discharging your batteries beyond the DOD can shorten its lifespan. The system voltage is purely the owner's choice, but as a guide, a 12 volt system is mostly suitable for small installations around 1200 watts and below. A 24 volt system is for medium-sized installations between 1200 watts to 2400 watts. And a 48 volt installation is for larger systems above 2400 watts. Please do know that for a 12 volt system, will draw more current as it needs to compensate for its lower voltage. So higher current means you need to provide thicker cables, and cables really aren't cheap. In this example, we will use a 48 volt system. Yeah, suppose we have a battery with a 12 volt output here and a battery capacity rating of 250 ampere hours, a DOD of 50%, and an efficiency of 85%. Now, to compete for the required battery capacity, the daily power consumption is divided by the product of the battery's depth of discharge and efficiency and the system voltage. So that will be 5 kilowatt hours, divided by 0.5 times 0.85 and times 48 volts. So the required battery bank capacity would be around 245.69 ampere hours. Now, to determine the number of string and series configuration for our battery bank, the number of battery strings can be determined by dividing the required battery capacity, this one right here, by our battery's rating. So that would be 245.69 ampere hours divided by 250 ampere hours. So that would be 0.98, or just one string of battery. Now, to compute for the number of series, it can be determined by dividing the system voltage by the battery's rated voltage. So that would be, our system voltage is 48 volts divided by the battery's voltage rating, which is 12 volts. Now we have the number of series for our battery will be 4. Yep. So this is how you configure your battery. So this is one string right here, and the number of series connections is 4. Step 4, sizing our inverter. So for an off-grid inverter, it is important to take into consideration the surge power generated by the load. For this, let us make a table similar to our load analysis, but instead of listing down the duration of operation, we will replace this by a multiplier. For motor loads such as the fan, the fridge, and the washing machine, we will multiply its power by 2 or 3. For lighter loads such as the LED light, the multiplier would be 1.3. Surge power is the sudden increase in power when you switch on your appliances, especially your motor loads. In this example, we have assigned the fridge and washing machine with a multiplier of 3. This one. The fan, which is a bit smaller than the washing machine, we assign a multiplier of 2. And for the rest of the load, we can assign 1.3. Yeah. So next is we multiply the total power by the multiplier. So we have a total power here considering the surge power. We sum this all up, and this will now be the minimum power rating of our off-grid inverter. So using that value, around 2 watts, 2 kilowatts, we can pick an off-grid inverter higher than this. So in this example, we have chosen a 3 kilowatt off-grid inverter. Since this inverter, its power rating is greater than the minimum inverter, power that we have calculated from the previous slide. So this inverter is okay. Step number 5, that will be sizing the solar charge controller, or SCC. So in step number 2, we chose a 380 watt solar panel with an open circuit voltage of 48.8 volts and a short circuit current of 9.94 amps. Now suppose one of our options for a solar charge controller is this, with a V maximum rating of 200 volts and a charging current of 50 amps. Now let's determine the series and strings configuration of our solar panels and see if our configuration fits the solar charge controller of our choice, this one. Okay, to calculate for the number of solar panel series connections, divide the Vmax, which is 200 volts, by the open circuit voltage of the solar panel, which is 48.8 volts. Result now would be 4. So we need 4 pieces of the solar panel connected in series. Next, we compute for the strings, for the number of strings. We divide the number of solar PV panels we got from step 2 by the number of series connections. So in step 2, we have computed that the number of panels that we require to support our load would be 4, divided by the number of series, which is also 4. So the number of strings now that we will need is 1. So next one, we will compute for the charging current of our solar charge controller. So this value depends on the amount of current produced by our solar panel array. And to compute this, we multiply the short circuit current of our solar panel, which is 9.94 amps, by the number of strings which we have calculated, which is 1 right here, and multiply that by 1.25 as a buffer. Yeah, and the resulting charging current would now be 12.425 amps. Okay, this will be the amount of current that will be charging your batteries, your battery bank. I'm sorry. So this ICC of 12.425 amps, this is less than the rating of our solar charge controller, so we can definitely use this SCC for this setup. Okay, now that we have all the things that we need, let's build our off-grid system. A typical schematic of an off-grid system, off-grid solar power system setup, will be something like this. So we have our solar panel array right here. This converts the solar energy to electrical energy. The solar array is connected to the solar charge controller. The SCC is connected to the battery bank. The SCC allows the electrical energy produced by the solar array to charge the battery bank. So yeah, but the main purpose of the SCC is to control the current that charges this battery bank and prevents the overcharging of the batteries. Next is the battery bank is also connected to the inverter, which converts the DC energy from this battery bank to AC to be used by our common home appliances. So in step 1, we did a load analysis and calculated our daily power consumption to be around 5 kilowatts. In step 2, based on the daily power consumption, we have calculated that we need 4 pieces of this 380 watt solar panel. In step 3, based on the daily power consumption and a battery with a voltage rating of 12 volts and a storage capacity of 250 ampere hour, we calculated that we need 4 of these batteries connected in series and only 1 string. In step 4, we have calculated the minimum inverter rating based on the load and its surge power. So the computed load power with the surge considered is a little over 2 kilowatts. Around 2 kilowatts. So with this, for this example, we picked an off-grid inverter that can withstand this and chose a 3 kilowatt off-grid inverter. In step 5, we have determined our solar charge controller, or SCC, based on the configuration of our solar array. Our 4 solar panels will be connected in series and only one string is needed. We calculated that the current output of the solar PV array wait, I think there is an error. Yeah, it's okay, it's fine. Yeah, so in step number 5, so we have computed that the our short circuit current flowing through the solar panel is 9.94. We multiply that by the number of strings, our solar panel strings, times 1.25. So the current output of the solar panel array is around 12.425 amps, and the voltage output is 195.2 volts. So these values are within the operating voltage and current of our chosen solar charge controller. Now that we have all the values of our major components, we shall now move to calculating our circuit breakers. For the DC circuit breaker, DCCB number 1, at the output of the solar PV array, we can calculate this by multiplying the short circuit current, 9.94 amps, by the number of strings times 1.25. So we the DC current flowing through this would be around 12.425 amps. In this case, we'll since we don't have any exact circuit breaker with this value, which we will now choose our circuit breaker with a rating with a rating with a higher value, next available higher value. In this example, we will choose a 14 ampere trip 2-pole DC circuit breaker. For the DC circuit breaker number 2, the output of the SCC going to the battery. The current flowing through this is the charging current going to our battery bank, meaning that will also be this one. The same current will be also the one flowing to the battery bank. So that's 12.425 amps. Same as this DC circuit breaker number 1. We chose a DC circuit breaker of the next available rating. That will be 14 ampere trip 2-pole DC circuit breaker. DC circuit breaker number 3, located at the output of the batteries and at the input of our DC to AC inverter. To compute this, we will divide the power rating of our inverter divided by the system voltage. So that's 3 kilowatts divided by our system voltage is 48 volts. So the current flowing through here is around 62.5 amperes. So in this example, we chose a DC circuit breaker with a rating of 70 ampere trip, 2-pole DC circuit breaker. And lastly, the AC circuit breaker. The output of our inverter can be computed as the maximum power rating of our inverter, 3 kilowatts divided by the our grid voltage, which is 220 volts. So there's an error here. This should be AC. Current AC, IAC, is 13.64 amperes. In this example, we chose an AC circuit breaker with a value of 15 ampere trip, 2-pole AC circuit breaker. So the other accessories are that I have not discussed is this DC isolator and the DC SPD. This DC isolator is it functions like a switch that you can manually operate to turn on and off or isolate certain parts of the system. So in this case, we are this switch isolates our solar panels from the rest of the system. Next one is the DC SPD, or the surge protection device. So this item, it protects your system from current surges by directing the surge current to flow to the ground instead of going to your equipment.